Hello, dear colleagues. I would like to tell you about a remote fiber optic sensor for controlling gamma radiation of various power. In modern world are constantly being posed new tasks for the solution of which is required the use of radioactive materials. Every year the number of the use increases, especially in nuclear energy and in scientific researches. Main difficulties appear with the control of powerful radioactive radiation, for example, in the areas of nuclear reactor. In these cases, control radiation situation must be carried out continuously in automatic mode. In some cases, control should be realized in the distance more than 10,000 meters from the location of the center of laser transmitting module and photodetector. One of the perspective directions for the implementation of remote control of radiation level is the use of fiber optic sensors. The fiber optic sensors developed nowadays, which operation principle is based on the measurements of change in radiation-induced losses or laser radiation polarization under the gamma radiation influence, have several disadvantages. At high exposure dose values, laser radiation in them is completely damped and sets to stop its work for a long time. The relaxation processes without interventions takes 10 to the fifth power seconds and more, because for measurements are used small hours. The use of more powerful radiation doesn't allow to conduct measurements with small exposure dose values and can damage photosensitive layer in photodetector model. Therefore, the purpose of this work is to develop a new design of a fiber optic sensor based on the research carried out, which will make it possible to carry out the measurements losses of long term to time. The E-centers appear in an optical fiber after gamma radiation influence. The E-centers are appeared as the changes result in the structure of the optical fiber. The amount of these defects directly depends on the two defects in the optical fiber, which are appeared after irradiation. There are displacement and ionization effects. The displacement is the atom's shift under the gamma radiation influence. It can lead to the destruction of the optical fiber structure. This effect can become irreversible at a high exposure dose of radiation. The optical fiber will be destructed at the area of the gamma radiation influence. Analysis of the experimental results obtained earlier showed that it's necessary to provide additional researches of gamma radiation influence on the optical fiber for developing new design of the fiber optic sensors. To carry out the necessary research, an experimental setup was developed and assembled. Its block diagram is presented. At the block diagram, you can see number 1 is the laser transmission module, number 2 is the power driver, number 3 is a polarizer, number 4 is the optical divider, number 5 is the optical power meter, number 6 is a multiplexer, number 7 is a pulsed semiconductor laser, number 8 is a pulsed power driver, number 9 is a source of gamma radiation, number 10 is a control unit of the source of gamma radiation, number 11 is the optical fiber, number 12 is a closed volume of polymeric material. Number 13 is a device for changing the temperature. Number 14 is a device for controlling the dose of radiation. Number 15 is a receiving optical module. And number 16 is the optical adapter. In contrast to earlier researches provided by other scientists, the use of the developed experimental setup makes it possible to measure losses both at the moment of the gamma radiation influence on fiber and immediately after its ending. There is no large time interval between the time of the gamma radiation influence and the beginning of measurements. It allows to establish a number of new features for optical fibers which relate to the color center's relaxation. For providing researchers in the experiment setup is used modified transmitting model company dials. A wavelength is 1550 nanometers. Variation of radiation power is from 0.1 to 5.4 milliwatts. Radiation-induced losses are determined with using the following formula, where Pin is the power input into the optical fiber, Pout is the power output from the optical fiber, and L is the length of the optical fiber. For using formula, were calculated losses, which appear on the connecting elements and different converters in the experimental setup. To implement different connections, we use detachable connections, which have typical losses 0.2 dB. There are 11 such connections. The losses in the optical adder are 0.46 dB. There are two such adders. The losses on the optical polarizer are 0.32 dB. Total losses are 3.44 dB. For registration in the experimental setup was used the receiving optical module by company Dallas, which is highly sensitive in the wavelength range of from 980 to 1650 nanometers. The user set of two devices from one company in the focal systems allows to obtain a high signal-to-noise ratio of the registered optical signal at a low power of laser radiation. At the figure 1, as an example, are presented the dependencies of the losses in single-mode fibers with the exposure dose of gamma radiation. Obtained results show that an increase in alone percentage increases formation velocity of E centers in optical fiber under the gamma radiation influence. The sensitivity of optical fiber increases to the change of exposure dose. It allows to register the changes in small exposure dose values, which lead to the decrease of the laser radiation power at the output of focal by 0.2 dB. At the figure 2, as an example, are presented the research results of velocity of the optical properties recovery after gamma radiation influence with a dose of 100 Gray. Analysis of the obtained results shows that optical properties recovery becomes faster with an increase of a percentage of its core. Therefore, in the work, it was proposed the following design of fiber optic sensor. An optical fiber with pure quartz core is proposed to connect through optical connectors to an optical fiber 200 meters long, with a core of silicium oxide and germanium oxide and alloying percentage of 20%. The alloying degree can be changed depending on the solving tasks. To recover the optical fiber properties in work uses a method developed earlier by us for trunk focal, with using an additional laser radiation with a wavelength 1310 nanometers. As the figure 3 and figure 4 are presented the research results of velocity of the optical properties recovery after gamma radiation influence with a dose of 100 Gray for pulsed and continuous laser radiation of various power. In the research was used pulsed laser radiation with a duration 0.1 with various powers during 10 seconds. Analysis of the obtained results shows that the use of additional laser radiation allows to increase the relaxation velocity of E centers and recover the optical properties of an optical fiber in less than seconds. Moreover, it was established that the use of additional laser radiation for optical fiber recovery is more effective than continuous. It should be noted it's easier to realize higher power in pulse mode than in continuous. In addition, to determine the optimal operation mode for recover the optical properties of an optical fiber, the dependence of the change in losses with time was researched for various pulse duration of an additional laser radiation. For conducting researches was used a single-mode fiber with a core of silicium oxide and germanium oxide with a lowering of 1.5%. Exposure dose was 100 Gray. Additional laser radiation with a wavelength of 1310 nanometers and power 0.2 volt was input into the optical fiber. As the figure 5, as an example, is presented one of such dependencies. Obtained results show that the pulse duration of laser radiation with using meander does not influence a lot on the changes in the relaxation velocity of E centers. Main influence is exerted by the laser radiation power, which cannot be increased to infinity, because an additional laser radiation with a wavelength 1310 nanometers begins to influence on radiation with 1550 nanometers. It increases the measurement error when control small exposure dose changes. Obtained experimental results show that the fiber optic sensor developed by us can work in continuous mode for remote control and exposure dose of radiation from 0.1 to 1000 Gray. The use of this design allows not only to register the presence of the gamma radiation in certain area, but also to obtain data about radiation via focal. The new developed fiber optic sensor will be in stable mode of radiative release. This will make it possible in the future, after additional research, to develop a remote system for large area state control of territories with an increased danger of pollution. Another promising direction for further research may be developed of a fiber optic sensor for continuous control to change the dynamic of the values of exposure dose in the central protective zone of reactor. Thank you for your attention.